Hello everyone, welcome to the summary lecture of week 5. Today we will talk about whatever we have so far covered in week 5 in lecture 13, 14 and 15, and then we will also talk about how do we apply whatever we have learned so far in this lecture 13, 14 and 15, how we use some sort of one case study of any particular location and try to look at some sort of statistical test. So, in this week 5 we have primarily talked about detecting and attributing changes in the extreme events. What is the detection? Particularly we are looking at if is there any changes which we are seeing happening in a particular location, whether it could be your temperature record or whether it could be your rainfall record. So, we are trying to look at whether we have any changes in your temperature or rainfall or any other meteorological parameter that can attribute to, let us say, climate change processes, or let us say human induced processes, or let us say natural variability processes. So, in the detection we have primarily talked about so many types of different statistical tests. Then in the later part of this week we have also talked about what is the attributional changes. Suppose now we have in the time series detected there is a statistical changes in the properties of time series. Let us say there is a jump of time series. Now how we can relate this jump with certain other processes which are responsible? How we are very sure that if there is a jump in the time series data set, it is because of the land use land cover change in a certain location, or it is because of tropical cyclone, or it is because of some sort of heat waves, and that produce a massive wildfire events like that. So, that is called attributional change, where we are looking at how do we calculate what is the fractional or probabilistic role of human activities in certain processes, and then we can quantify in number, so that we can compare it and we can suggest whether if there is something has been changed, it is primarily because of the human activities. So far all of these concepts we have already covered, and in this particular lecture we will see one by one all this concept, so that we can revise it, and then towards the end we will have some sort of assignment. So, in the beginning of the lecture 13 we have talked about trends in the data. What is trends? Trends is generally defined as a a long term trend, increasing or decreasing trend, or let us say in which direction your time series is moving, whether it is positively direction, whether it is continuously increasing like that, or whether it is continuously decreasing, or it has been some sort of delay period and then continuously increasing, and after that it continuously decreasing. There are so many possibilities are there. So, therefore, in your time series data set we will look at basically the long term changes or increase or decrease in the data set. What are the methods? We can talk about moving averages, which are basically smooth and short term fluctuations to highlight long term trends. So, moving averages, like let us say you have a time series for 100 years, then you can take 10 years as a moving average, and each 10 years you collect the data and take average, and then you make that moving average as a sliding window, and you add one more here, and then you just remove it in the previous step, and that basically the way you basically slide the window using the 10 year and can calculate the averages, and then you can plot it for individual years. So, that is basically we can do that for moving averages, and that is basically highlights the long term trends. Then we can talk about linear regressions, fitting a linear straight line in the data or estimate the trend, what is the slope of the trend, what is the strength of the trend, like that. So, these are the processes where we can apply in the model data set, and we can try to find out what is the straight line or linear regression in the data. Then we can apply the MK test, which is called Mann-Kendall test. Mann-Kendall test is called non-parametric test. Non-parametric test is basically those tests which do not assume any kind of distribution prior to that particular time series data set. So, these are distributional free test, where we don't assume any distributions, and then we apply it in the data and try to look at whether we have any monotonic trends. It is continuously increasing, it is continuously decreasing, or without, if there is no trend at all. For example, here you can look at these are the rainfall values, and we have applied some sort of man candle test, and we found a linear line which can tell us about is there any trend in the data set, what is the overall confidence interval in the that trend, or let us say what we have a continuously decreasing trend, whether the rainfall is continuously decreasing, like that. So, these are the pattern we can identify using these kind of the test, and we can find out what is the slope, and more importantly whether the trend exists in the data set is statistically correct or not, statistically significant or not. So, this is what we can do using these types of analysis. Then towards middle of the section, we have also talked about seasonality in time series. Suppose we are collecting the monthly rainfall data set, or monthly temperature, or monthly humidity, or monthly runoff, or monthly multiple types of data set, where we have some sort of seasonal fluctuations. During the monsoon we have higher rainfall, during the pre-monsoon we have lower rainfall, like that. So, this way we have a seasonality in data set, and that is very important to assess that, because seasonal behavior can reveal multiple things, whether the seasonal behavior remains same, or it has been also changed because of some of the processes, or we have some sort of very different anomalies we are observing from the data set, like that. How do we do that? We can use Fourier transformation. We basically transform or decompose our time series into frequency domain and try to look at those frequency component. That is one of the best good approach which can be used for identifying the frequency of the time series. The another is called the seasonal decomposition of the time series, where we look at how seasonal fluctuation is there. We can decompose our time series into different trend, seasonal or residual component, and then we can look at it. What is their seasonal trend, what is their behavior, what is the residual component behavior, and if there is any trend or not in the data set. Then we can also look at when we are talking about this kind of seasonal behavior, autocorrelation function analysis, where we are not using we basically use the lagged version of our time series, and we try to correlate with different lags, for example 1 day, 2 day, 3 day, or 1 month, 2 months, 3 months, 10 months, like that. And then we can calculate what is the correlation we have higher for different months. That basically set up that okay, this has basically correlate with your 5 months delay, some other parameters, like that. So, that is basically can be also be done to identify the seasonal behavior in the data set. So, there are 3 primary methods where we can do that. Fourier transformation is frequency domain transformation, seasonal decomposition of time series STL, and autocorrelation function analysis, like that. Then we have also talked about correlation analysis, which is very important. Let us say there are certain processes which might influence the rainfall extreme in a certain location. What we can do, we can take the time series of the rainfall extreme of that particular location, and we can also take the climate variables which might influence the climate extremes. Then we try to look at plot some sort of XY scatter, where we have x axis, y axis, and then we try to put all this data set in this way. Not in this way, but we try to plot the data. If it looks like this way, then it is basically reflecting that the trend is your linearly increasing, which means a one positive correlation is there. If there is a sort of a decreasing trend, which means x is increasing, however y is decreasing. In this case x is increasing and y is also increasing, therefore we call positive correlation. When we have x is increasing or y is not increasing, although it is decreasing, it is called negative correlation. Or when we have there is a no correlation at all, we do not have any significant line or particular line which basically tells about the slope or one-to-one correlation between these two properties. So we have a climate variable, we have a climate process which might influence the climate variable, we can relate with some sort of correlations, and then we can try to find out. One of the very important thing is here, it might possible that whatever the value we are taking as x and y, is not related, might possible that they are not related to each other at all. And even though they give you a good correlation, which does not mean that x is influencing y or y is influencing x. We have to be very sure about the process understanding, causality analysis. So, what is the causal behavior between x and y, then we can use these correlation analysis to infer the results. Without causality, there is no correlation. Without any causality, if you are talking about correlation, which means it's just we have got some results, but there is no physical interpretations like that. So, this is what it is important. We have to do some sort of correlation analysis to look at what is the strength of correlation between multiple different processes. Then in this lecture 14 of week 5, we have talked about data preparation for analysis. So, it is very important. Let us say we are talking about multiple statistical analysis, frequency analysis or seasonal analysis. The data preparation is very important, where we are looking at the different types of data set, climate data or reanalysis product or weather station records or satellite based management, and we basically use in the data preparation analysis by applying the pre-processing steps, where we are talking about data cleaning. Let us say if we have more outlier, we can remove those outlier. If we have gaps in the data, we can try to fill the gaps in the data or like that. Or data consistency, if there is any problem with the error or some sort of data resolution error or the temporal consistency required, we need to do that, so that we can have a consistent data set. Or readiness for analysis, let us say we have to store the data in such a way that it can be easily readable for different programming language, also different for certain softwares like that. So, this is what is very important. So, where we have data collection, data processing, data cleaning, that can be used for exploratory data analysis, and that is also be used for modeling purpose. Once we have done the modeling, which the results we obtained from the modeling practice, we basically try to look at their visualization and reporting of the results, and then we try to deploy or implement certain strategies based on our data analysis like that. Then we have also talked about fitting the generalized extreme value or generalized Pareto distribution model. So, suppose we have a rainfall measurement of a certain location since 1950 to or 1900 to let us say 2020, and then we divide our data into 1900 to 1960 and 1961 to 2020. So, this is the 60 years or record and 60 year post 60 records like that. We can compare the extreme behavior of pre and post 60 data set by fitting the GEV model separately, and then we can compare. What is the advantage of this? We would be able to find out what is the extreme magnitude, what is the extreme frequencies, and whether is there any change in the extreme magnitude or frequencies which we have seen because of the climate change. So, this kind of detection and algorithms can try to look at the changes in the frequency domain and try to give you the more detail in information about what is the magnitude change, and what is basically, if let us say the GEV distribution gives you the safe factor is greater than 0, which is a Fritchett. Let us suppose data set pre 1960 gives you eta value is less than 0, which is your Weibull distribution. But post 1960 data set gives you Fritchett distribution, which means the heavy tail distribution has been dominating now, which means if this is a heavy tailed, which means the probability of occurrences of the extreme events has been already increased, and therefore it is a kind of a heavy tailed. If you compare to the original conditions where we have light tailed distribution, but post 60 it is kind of a heavy tail distribution. So, this way we would be able to analyze the changes in our time series data set and probabilities and magnitude and their correlations, relationships like that. Then we have also talked about change point analysis, where we have talked about, suppose we have a time series data set and there is sudden change occurred in a time series because of some processes, how do we detect that? So, let us say we have collected the rainfall data or flow data or temperature data, something like that, and then we try to look at how the statistical property has been changed from one particular year after 1 year. So, what is the advantage of this? Let us say you are talking about the floods in a certain region. Floods are increasing. Let us say 1978 or 80, after that we have significant rise in the floods magnitude. So, we try to look at what has happened in the upstream location of that catchment, whether the land use land cover has been significantly changed, or let us suppose we are saying that the flood magnitudes or the peak of the magnitude has been significantly depleted after certain years. So, is there any kind of a infrastructural development happened upstream, or is there any kind of a meteorological parameters which are interacting with these processes that is the responsible for change in the behavior. So, change point analysis primarily we look at from which point of time a time series has been significantly changed its statistical behavior, that is called change point analysis. Then in the lecture 15 we have primarily talked about the attribution analysis. What is attribution? We try to so in the previous lectures we have tried to look at the detection, how the climate has been changed because of the certain different processes, and then we try to look at what is the role of human. For example, what is the role of climate, what is the role of natural variability, or what is the role of indirect human activity on certain weather related or different surface processes. So, the attribution is primarily we try to quantify the human influence on specific weather or climate events. We try to answer, let us say, did climate change make an event more likely or severe, and what proportion of an event risk is due to human activities. These are the primary questions we are trying to answer using the climate attributional studies. So, we have talked about let us say we have temperature measurement of global temperature, local temperature, we compare these temperature whether is there any significant change in the temperature, then we try to look at the statistical behavior or model based assessment, and we try to figure it out whether it is because of the primarily natural variability or human contribution. Once we establish this fact, we can switch off one particular parameter and try to compare again, and then we can try to look at, okay, now what will happen if we switch off the human part, whether the natural variability alone can define the local temperature rise in a certain region, or if you just add the human activities, then it basically defines. So, that makes everything will be crystal clear that okay, human activities are the major processes which are responsible for these types of changes. Then we have in the lecture 15 talked about how do we calculate the fraction of attributional risk. It is a probabilistic method where we are talking about probability of occurrence of natural events and probability of occurrence of the actual events. We take the ratio and subtract by 1 minus this ratio, and then we calculate FAR. So, once we calculate this FAR, we can basically attribute that okay, what is the role of the human activities in certain processes. Suppose there is a two different time period data set or simulation data set, we can calculate the probability of occurrence, and then we can calculate what is the role of so a human has doubled heat waves, human has doubled or tripled flood intensities, or human has tripled let us say drought durations, or flash drought has been occurring more frequently because of the human activities. So, these sort of the analysis can be done by these kind of processes. Then observational evidence for attribution we have also talked about. So, let us say we can use the remote sensing data set, we can use the paleoclimate data set, we can use the instrumental record to look at what has been the data is behaving historically, and what would happen after 1960, 1970, 80 like that, whether the human role become more significant, whether is there any change in different parameters, for example, your observed greenhouse gases, ozone or land cover or aerosols like that, or what is the role of human activities, what is the role of natural activities, and what is the role of, if combining natural and human altogether, what is the overall role of these types of activities like that. So, this is what we can do that using the observational studies. For example, here it is very clear, if you look at the temperature difference from the average, the natural variability cannot explain the observed data set, observed rise in the temperature. But if you add the human driver plus natural driver, it can certainly detect the slope of the change in the temperature, which can provide a clue that human is the dominating cause of the temperature rise globally, and therefore we have a rise in the temperature all across the world like that. So, this is what we call the attributional analysis, and therefore we would be able to use this analysis for further attributional evidences. What is the limitation? Of course, data availability, regional variations, that might play a major role. We have to take care of these things, and let us say limited length of the high quality observational record, that might also possible to play a very significant role. So, to solve these issues, we have to fit the model, do the model calibration and validation analysis, and then we can try to look at how do we fill the gaps of the data set, and after filling the gaps, or let us say extending the data set at certain lengths of the time period, and then we can further use it for our attributional evidence based analysis or observational evidence based analysis for attributions. So, this is what we have so far discussed in this particular week. We have talked about detection of the climate extreme change, we have talked about attributional of climate change, and that makes this week we have to be we have learned about how do we very sure about if certain process or certain human led activities are primarily responsible for different types of changes in weather variables. So, what you can do in the assignment is, let us say you select any time series, any extreme time series. You can take extreme time series either from generalized extreme value distributions or generalized Pareto distributions. Generalized EV basically is coming from your AMS or block maxima types of approach. So, what is basically, you can take the extreme time series data set, and then you can try to look at where we have a significant change in the data set, where is there any change point exists in the data set, and if you can calculate it. So, there are multiple tests, let us say Petite test you can apply, or you can simply use two probability based model, and we can compare the CDFs or PDF change in the behaviors like that. So, you can calculate the change point in the extreme time series data set, and then you can also try to look at how do you can correlate, let us say extreme time series data or temperature data or rainfall data with global variables. For example, you can talk about global temperature, you can talk about CO2 concentration or ENOC index, and how these global fluctuations or global perturbations are interfering the climate behavior of a certain regions, extreme time series of that particular regions like that. So, you can try it using whatever we have discussed so far in the previous assignment. How do you calculate or estimate or get the observational time series data set, and based on that time series data set you can basically try to look at these proxies. For ENSO, global temperature, CO2 concentration, these are online available. You can download the time series of these data set and you can try to correlate with our data. So, this is all about lecture week 5. In the next lecture, we will primarily talk about how do we solve this assignment of week 5, and then after that lecture we will basically move to week 6 of climate change and extreme events. Thank you so much for your attention.